Look closely at sand. Whether you use it for building epic sand castles, telling time with a classic hourglass, or complex hydraulic fracturing, sand is pretty much the exact same stuff just about everywhere you go. It's simply an uncountable number of tiny, identical grains mixed together, forming the exact same sprawling dunes and endless sunny beaches across the entire globe. But wait, why does sand almost always look exactly the same? And how on earth does so incredibly much of it end up sitting at the beach? Well, much of the world's sand is made out of the exact same stuff. Billions and billions of tiny crystals of the mineral quartz. Quartz is a simple chemical combination of silicon and oxygen, which conveniently happen to be the two absolute most common elements in Earth's crust. And as Jack here knows, if you've ever bitten through the crust of a beach sandwich that had some sand in it, you'll know firsthand that quartz grains are incredibly tough. Say goodbye to that tooth, Jack. So why is quartz so incredibly tough and so perfectly sized? Well, quartz crystals originally form within massive, cooling blobs of molten granite rock, or magma, buried incredibly deep under the Earth's surface. As the scorching hot magma slowly cools down over millions of years, different minerals inside the magma begin to crystallize into solid rock at different temperatures. Interestingly, quartz is actually one of the absolute last minerals to form. Because it's late to the party, it's forced to crystallize in the tiny, microscopic spaces left over between the other rocks, which pretty much ensures that nearly all quartz ends up in a very specific, tiny size range. But being the last one to form actually has some massive, lasting advantages. Minerals that crystallize in the earlier, much hotter conditions develop much weaker chemical structures. When they are finally exposed to the elements on the surface, they weather away very quickly. It's kind of like how a rapid relationship forged in the intense heat of passion might not be quite as stable as a deep, strong bond developed slowly over a long time. So as those weak, flash-in-the-pan minerals weather away and crumble into dust, the unfaltering, tough little quartz grains are simply left behind, literally popping out of the rock as sand. And then it's only a matter of time, sometimes a very, very long time, before that loose, quartz sand gets whisked away by rushing streams and powerful rivers, as the sand is aggressively tumbling down the river for hundreds of miles. It grinds against rocks and riverbeds, perfectly polishing the grains into those smooth, round shapes. Finally, the rushing river carries all that tumbling sand directly to the sea. There, at the mouth of a river, the fast-flowing water slows down very abruptly. When the water loses its speed, it instantly drops the heavy, well-rounded quartz sand straight to the bottom. Now, the larger rocks and heavy pebbles were already left far behind upstream, while the incredibly tiny, microscopic sediments like silt and clay are incredibly light. They continue to be swept far along by the weakened ocean current, depositing miles away from shore. Over thousands and thousands of years, the shifting paths of these rivers sweep up and down the coast, constantly dropping off massive piles of quartz sand. That sand is then perfectly spread out by the ocean's waves and currents, forming smooth, beautiful sandy beaches. Of course, not all beaches are purely quartz sand. Some are made of crushed seashells, volcanic rock, or colorful coral. And not all quartz sand ends up on beaches. Some is blown into massive desert dunes. But the fact that so incredibly many beaches look exactly the same is a beautiful testament to the delicate chemistry of the cooling Earth's crust, and to the brutal physics of shifting rivers constantly surging toward the sea. They are quite literally the real sands of time.